As far as address multiplexing is concerned, we have got 8051 when it is connected to one external program memory, that is EEPROM. So, this is the external address bus from port 0. So, we have got this port 0, so port 2 is providing the higher order address bus A8 to A15 bits. Port 0 is the multiplexed address data bus. So, this is passed through one 74373 latch for multiplexing, for demultiplexing the lower order address bus, and the ALE signal is connected to the G pin of 74373, by which we can when this ALE signal is activated, address is available in the bus and that gets latched here. So, as far as this EEPROM is concerned, so it continually sees the address bus address bits A0 to A7, A8 to A15, and when this PSEN bar line is activated, so it is connected to the OE bar pin of this EEPROM chip. So, OE bar is same as read bar, as we said. So, it is output enable or read bar line. So, when these lines are given, so EEPROM will put the content on the data bus and the data bus through port 0 will reach 8051. So, in this way we can connect external program memory to the 8051 chip. So, we also call it external code memory, because this external program memory is generally holding the program. Of course, in some cases you can connect, you can put the data there as well, but for generally, so that will also be treated as code only. So, if we look into the timing diagram, so if this is the oscillator clock that we have, so we have got this ALE signal. So, they are activated at this point. So, when the ALE signal is falling, so at that time the PC, the port whatever on port 0. So, this lower order address bits will be put and that will get that will be sensed here. So, that will get latched at this point, and when after that this PSEN bar line will go low. So, when this PSEN bar line goes makes a transition from low to high. So, that is taken as the point at which the data bus will have the opcode available. So, at this point, so in between this activation of PC low and this activation of this PSEN bar. So, memory is expected to put the opcode onto the data bus. So, opcode will be available anytime like this, and when this PSEN bar line makes a transition from low to high, then only the opcode will be taken off by the memory. So, it is the protocol, the memory should keep the opcode available for that much amount of time, and then this 8051 will sense this opcode through this PSEN bar line, and this value is read here. Again, after some time the ALE signal will go low, and when it is going low, so it will be used as the value to latch the lower order address bus onto the lower order address on the port 0, that lower order address bus. So, you see that these signals, when they are falling, so they are used for sensing the values, or similarly this ALE signal is when it is making the transition high to low. So, they are actually taken as the triggering point, and this PSEN bar line. So, when it is, since it is PSEN bar, it is this complementation is there. So, when it makes a transition from low to high, so that point is taken as the triggering point for the memory to put the data. Okay. So, this way this whole operation takes place, the external code memory access reading takes place in this fashion. On the other hand, if we look into the data memory connection, external data memory connection, then we have got the connection like this. So, here also, so we have got one, say suppose we are going to connect 1 kilobyte of RAM. Okay. Suppose the RAM we are connecting is only 1 kilobyte long. So, we have 1 kilobyte means, so the RAM will have 10 address lines. So, this lower order address bus, that A0 to A7, they should be connected, and this A8 and A9. So, this memory chip has got 10 address lines A0 to A9. So, A0 to A7 will come from port 0 through this multiplexing through this demultiplexing of the address bus by 74373, and this A8 and A9. So, these two are coming from the port 2's bit number 0 and bit number 1. So, the rest of the bits are not connected. So, as we know that it may lead to folding and all that. So, we will not go into that. So, other bits being do not care. So, that can lead to folding. Then the read bar line that we have. So, read bar line is connected to the OE bar or output enable of this RAM chip, and the write bar line is connected to the write pin of the RAM chip. So, there is no other decoding done. So, this CS bar pin is grounded. So, this RAM is always enabled. So, whenever the address is put onto the address bus and this signals read bar or write bar is given, the content of the memory cell will be available on the data bus to be read by port 0. So, apart from that, this PCN bar line will have no connection. So, if you are not having any external EEPROM, then this PCN bar will never be connected, and this if it is if the EEPROM is there, then that PCN bar line may be connected to the EEPROM. And this EA bar line also the external access. So, that is connected to high, because this is not doing an external access as far as the code is concerned. This is not code access. So, this is data access. So, there is no problem. And the timing diagram again, so this external data memory access is done by the MOVEX instruction. We will look into this MOVEX instruction in detail later, but essentially its format is something like this. So, it is like MOVEX @ DPTR, MOVEX @ DPTR comma A, or another option is the other way. So, it is for getting the data from A register into a memory location pointed to by the DPTR register pair. And there is another version for storing for getting the content of memory location to the accumulator. So, there you just write it as MOVEX A comma @ DPTR. Okay. So, those are the two versions of the MOVEX instruction. So, they are for external data memory access. For external data memory access, so it uses the MOVEX command or MOVEX instruction. So, how does it operate? So, you see that first it has to get the instruction from memory. So, for that purpose, so assuming that this opcode this instruction is in the external memory. So, this is this PCN bar line is activated, so that you get the opcode from the external ROM, external EEPROM. So, that is this part we have already discussed, how to access this external ROM. So, ALE signal is activated, the address is given, lower order address is given, higher order address is put on the PC high, and this PCN bar line is given. When PCN bar is going high, the data the opcode MOVEX opcode is available onto the data bus. Then the decoder will decode that MOVEX instruction, and now it will go into the second stage, and in that second stage it has to it puts the read bar line. So, DP high, the DPTR register, it is consisting of two pairs, DP high, DPH and DPL, two 8-bit register, whereas DPTR is the 16-bit register. So, this DP high, so that will be put on to port 2, because through that this external address bus will be connected to the external RAM. So, it will be put there, and this DPL, so this is again multiplexed with data bus. So, that is the port 0. So, this value this lower order address bus is multiplexed. So, in the lower order address bus put the value DPL. So, higher order address bus has got the content of DPH, lower order address bus has the content of DPL, and then this read bar signal is activated. When this read bar signal makes a transition from low to high, by that time from the RAM, external RAM, the data should be available onto the data bus. So, on this rising edge the value will be picked up by the 8051 chip, and again so that is the complete so MOVEX instruction is complete. So, data is since it is basically reading the content of memory location into A register. So, read bar signal is given. Similarly, if you want to write, like if you want to write the content of A register onto external data onto external memory. So, in that case write bar signal should be given, and here instead of coming from external data input, it will be from the A register, the accumulator register. So, this how this connection is done, like external code memory. So, for external code memory connection, so we have got this higher order address bus P provided by port 2. So, P 2.0 to 2.7 they are connected to A8 to A15. Then port 0 provides the multiplexed address data bus. So, this 8 bits they are connected to the data bus of the RAM chip and data bus of the ROM chip, and also it goes to the latch 74373 latch, where it is demultiplexed by the ALE signal. Okay. And so, this is the demultiplexed address bus, this is the demultiplexed data bus. ALE signal is connected to the G pin of 74373, PCN bar line is connected to OE bar, and CS bar line is grounded, and this EA bar line is grounded. So, that is, it does not have any meaning because it is not the data access. So, it does not have any meaning. So, for external data memory access, so this is the thing, that is write bar line is connected to write bar, read bar line is connected to read bar. PCN bar, so PCN bar is not necessary in this case, so the connection is not shown here, PCN bar is not meaningful. ALE signal is connected to G. So, rest of the thing is unaltered. So, P0 to 7 goes to this this latching of this lower order address bus here, and the data bus is connected to D0 to D7. So, this EA bar, so this is connected to ground, meaning that this is the external memory access. So, this EA bar line is grounded. In the previous case also, this EA bar line was grounded because we were doing external memory access. Okay. So, in both the cases external memory. So, there will be some more detail where we will see how this EA bar line makes difference between this external access and internal access. So, since here we are doing external access, so EA bar pin should be grounded, and for that code memory access also, since we are doing external memory access, this EA bar line should be grounded. So, next we will look into how can we overlap this external code and data spaces. So, this is very simple, because if you like, instead of using a separate EEPROM for storing the program, so many cases what happens is that we put with the microcontroller a single externally we put a single RAM chip, and in that RAM chip, so it acts both as program memory and data memory. So, for that purpose what we have to do is we take the RAM chip, and then this write bar line of the processor is connected to the write bar line of the RAM, and this RD bar and PCN bar they are odd, and they are that is connected to the OE bar line. So, whichever signal is activated, so RD bar or PCN bar, so both the cases OE bar line will get activated. So, this RAM will be providing the data. So, read bar is activated when it is doing say data access, and PCN bar is activated when it is doing program access. Since program and data both of them are residing in the memory in the RAM, so we need to access RAM in both the cases. So, this is a very common practice for systems that have got limited amount of external memory. So, we do not put separate ROM and RAM. So, we put a RAM that also serves the purpose of the ROM. So, this is how we do that overlapping. So, this read bar and PCN bar, so those two lines are ANDed and it is given to the read bar line. So, any of them being low, this read bar line will be low. So, we will get that corresponding signal here telling that it is read operation. Similarly, write bar line is connected to the write bar pin of the RAM. So, rest of the thing we have already discussed. So, this is the only additional thing that we have to do, this putting of AND of read bar and PCN bar for doing the overlapping of code and data spaces. So, what is the advantage? First of all, this overlapping of code and data spaces, it allows the RAM to be written as data memory. So, and read as data memory as well as code memory. So, while no, code memory is in general ROM. So, we do not write there, we just read the data, we just read the code from there, and the constants that we have in the program. So, they can also be treated as code, and those constants are also kept in the ROM. Okay. So, if you are using RAM, then for write operation, so you can use the write bar pin access, and then so we can write the values onto the RAM as data memory, and if you are trying to access the program, then you can use that pin bar, or if you are trying to access the data part of the RAM, then you can use the read bar line. So, we can, so what is the advantage of doing all these things? So, this will allow a program to be downloaded from outside into the RAM as data and executed from RAM as code. So, many a times what happens is that with this microcontroller based systems, so they have got interface with program with personal computers, and then there through a download cable we download the program into the onto the kit. Okay. So, the program is first developed on the PC. So, while we do the simulation and all that. So, when we are satisfied, we generate the object code for that program on the PC, and then that object code is downloaded onto the 8051 kit. And when we are doing this, so if it is ROM, then we have to go for programming of that ROM, and that is costly, because again if we want to change something, erasing will also become a bit difficult compared to RAM. So, instead of that, if we have got RAM to be used as the code memory as well, then we can just write the values onto the RAM. So, that way the entire program can be downloaded into the RAM. Okay. And then we can use that RAM both for program as well as data. So, if you look into the memory structure that we have, so the program memory structure is like this. So, we have got the total address space, total address line that 8051 has is 16 bit. Okay. So, that is address bus is 16 bit. So, the total address range is 0000 to FFFF. Now, so your access is from it starts with 0000 onwards. Now, if you make this EA bar equal to 1, so that means we are accessing from the internal memory, and if you make EA bar equal to 0, it will access from the data memory. So, in case of so if you do it like this, then what happens is that you have got this part. So, you can put your entire program in the external memory. So, that in that case we will make EA bar equal to 0, and this if you have got 4K address space, then this 4K sorry, so when EA bar is 0, your entire memory, external memory will be acting as the external EEPROM that we have. So, externally we connect 64K type of program memory, and then this through this pin bar line activation. So, this entire external chip will be accessed. Whereas, if you make this EA bar line equal to 1, then for initial access, so it will be using the internal memory, but after that it will be using the external memory. Once it finishes this maximum address, for example, in 8051 we have 4 kilobyte of internal memory, internal ROM. So, when this is over from the next address onwards, so it will be accessing this external memory. On the other hand, so this for data memory part, so we have got this 00 to FF. So, that much will be internal memory, and from FF onwards, so it will be accessing the external memory. Okay. So, from because only 128 bytes are there for the internal memory. So, first this 00 to 127, so it will be internal memory, and 128 onwards, so it will be accessing external memory, and that is detected by the MOVEX instruction. So, whenever you are using MOVEX instruction, so it will be using the external memory, and whenever you are using move instruction, so it will be using internal memory. So, we will see that there are two data movement instruction, one is move and the other is MOVEX. Okay. So, move is for internal access. So, this is internal, and there is a MOVEX instruction that we have seen. So, MOVEX is for external. So, if you are using MOVEX, then it will be using this external memory. If you are using move, it will be using this internal memory. So, that is the 8051 policy. Okay. So, so you can say in some sense I can say that okay, the total data memory that 8051 will have in that case is 64K here plus this 128 byte internal. So, this 64K external plus this 128 byte internal. So, that is the total data memory we can have. For the program memory side, it happens that if EA bar is equal to 0, then the total then it will be accessing for whenever it is accessing program. So, it will be accessing this external memory. Okay. However, if this EA bar line is equal to 1 and this maximum address is say 4K, then for the address range 0 to 4K, for 0 to 4K it will be accessing this memory, and when the address goes beyond this 4K, it will be accessing this external memory. Okay. So, if EA bar line equal to 1, then for address between 0 and 4K it will access internal memory, internal ROM, and beyond 4K it will use the external ROM. Whereas, if EA bar line is equal to 0, in that case for any address it will go to the external memory for getting the opcode or getting the instruction. So, that makes it very flexible. Okay. So, we can have we can configure this system as per our requirement. And many of the microcontroller development kits, so they do it like this. So, they just map this external the entire memory as the external memory only, and we can do that. Or in many in some other cases what is done is this EA bar line equal to it is made equal to 1. So, when it is accessing the internal memory, so that is made to hold the operating system code, monitor programs and all that, and the user programs are all in the external memory. So, it is also done that way. So, if we look into this on chip memory in more detail, so you can find that so there are so total we have got 256 bytes. So, out of that, so this 128 bytes, that is 0 to 7F. So, we will have some special feature, and remaining 80 to FF. So, we will have some other feature. Okay. First of all, 0 to 1F. So, we have got some general purpose registers. So, they are the CPU registers. So, unlike your microprocessor like 8085, so we do not have separate CPU registers, because now the memory, that the internal memory is also a part of the chip. Okay. So, there is no point keeping something in the CPU separately compared to the memory. So, that is why these registers, so they are nothing but some locations in the internal RAM. Okay. So, 00 to 1F. So, that is we have got this general purpose registers. Then the location 20 to 2F, they are called, they are bit addressable. So, you can access individual bits. As we know that the memory has got a word size. So, that word size is in whatever we have discussed, they are 8 bit word. So, if you are accessing a location, means you are accessing 8 bits at a time. But in many cases we want to access individual bits separately, and for that purpose there is a portion of memory which is bit addressable. So, this 2021 or 20 so there are some bit numbers will be given. So, we will see that. So, this location 20 is 8 bit wide, and each of these locations can be accessed separately, they can be set and reset separately. Then 30 to 7F, we have got this this is the scratch pad that we have. So, this is for some other purpose. So, you can use them as temporary locations, sometimes we use them as stack location, etc. So, it is done like that. And after that we have got some 80 to FF, those locations. So, upper 128 RAM. So, that is some extra RAM locations that we have. Okay. So, this where is this lower part? So, we can use both direct and indirect addressing. So, we can have only indirect addressing here, or we can have direct addressing for the special function register. So, we will explain them as we proceed. So, this is the first part, okay, the CPU registers that we talked about. So, the registers, so there are actually 32 registers, okay. And these these 32 registers, they are divided into 4 banks, bank 0, bank 1, bank 2 and bank 3. At any point of time, only one bank of registers is active, okay. So, this is the lowest bank having the registers R0 to R7, then we have got bank 1 going from R0 to R7. So, like that we have got different registered banks. So, this is that general purpose register bank 00 to 1F, and you can control this bank selection by 2 bits in the processor status word register, which are known as PSW 2 and 3. So, PSW is the processor status word register, its bit numbers 2 and 3, they can be used to select the register bank. So, this is helpful because what happens previously while discussing on 8085, we have seen that if we are going from program, we executing one program and an interrupt occurs, then it is the responsibility of the interrupt service routine to save all the registers that it is going to use in the body before doing any operation, because the program which got interrupted may be using those values, and again while going back it should restore all those register values before the return instruction. Now, that is costly because so many saves are to be done. So, what is so in this case in 8051 we have got the flexibility that we can just switch between the banks, okay. Maybe the main program is using bank 0. So, when we are in the interrupt service routine, so we can simply switch over to bank 1, so that all the manipulations that the interrupt service routine will be doing, so they will be affecting bank 1 register. So, bank 0 registers, they will remain unaltered. So, later on while coming back from the subprogram or subroutine, so you can just switch the banks again, so that the original bank gets restored. Okay. So, this helps in the context switching process. Okay. So, context switching becomes faster. So, since embedded application, so we want to have faster context switch to respond in real time fashion. So, this is helpful.